In this question we have a 555 timer IC where RA is given as 2.2 kilo ohm, RB is 4.7 kilo ohm and the capacitance is 0.022 microfarad, and we have to find out the frequency of oscillation at the output pin 3. So in 555 timer IC we know that the voltage of this capacitor voltage varies between VCC by 3 to 2 VCC by 3. The minimum capacitor voltage is VCC by 3 and the maximum capacitor voltage is 2 VCC by 3. When the capacitor voltage hits the minimum value, it starts charging and it charges through VCC. So the charging path is current will flow through RA, then RB, then capacitor, then in this case it will be charged through VCC, RA, RB, capacitor and ground. So the capacitor will charge towards VCC, the steady state voltage of the capacitor. If it is left to charge through VCC for infinite time, mathematically infinite time, the steady state voltage will be VCC. But when the capacitor voltage is 2 VCC by 3, it starts, here we have a discharge, so this is ground here. When the capacitor voltage is 2 VCC by 3, the internal circuit is such that this terminal gets connected to the ground, and now this capacitor starts discharging through RB and this ground. From this ground current will flow in this direction, so capacitor will discharge and the current will again enter to ground. Okay, so capacitor charges towards VCC through RA and RB. During charging, the time constant will be, it takes through RA and RB. So RA and RB are connected in series into C, and during discharging the time constant will be, it discharges through RB only. Okay, time constant will be RB into C. Okay, capacitor voltage discharges towards 0 if in this state only. If it is left for mathematically infinite time, the steady state voltage of the capacitor will be 0 and charging is towards VCC. If we draw the steady state voltage of capacitor VC, the minimum voltage is VCC by 3, maximum voltage is 2 VCC by 3. Let's say this line represents voltage VCC. Okay, so when the capacitor voltage is VCC by 3, this switch is automatically disconnected. Okay, now if this switch is disconnected, the capacitor will stop discharging and the capacitor will instead charges towards VCC. Current will flow in this direction. So starting from VCC by 3, it will try to charge towards VCC, and when it will hit 2 VCC by 3, this switch is connected and it starts discharging, and it discharges towards 0 volt. So after this point, first I am drawing the dotted graph. Its tendency is to discharge towards 0, but again when it will hit VCC by 3, it will start charging. So this way the graph of capacitor voltage will be periodic. When the charging of capacitor happens, output voltage will be high. When it discharges, output voltage will be low. So the frequency of output voltage at pin 3 will be equal to the frequency of capacitor voltage. The charging time constant is Ra plus Rb into C. Charging time constant is high, so the charging will be slow. Discharging time constant is low, so the discharging will be fast. Okay, and charging plus discharging time, this will give you the time period of oscillation of capacitor voltage, and 1 by time period will be the frequency of oscillation. So first let us find out the charging time. The initial voltage is V0 equal to VCC by 3. The steady state voltage is VCC. So V infinity is VCC, and let's say this is 0. We have to find out the duration in which the capacitor voltage will be 2 VCC by 3. So let's say this is T1. T1 is equal to 2 VCC by 3. Now we will apply this formula. Vt is equal to V infinity minus V0 into e to power minus t divided by tau. This we have studied in DC transient circuit. So at time t1 the voltage is 2 VCC by 3 is equal to V infinity is VCC minus V0 is VCC by 3 into e to power, time is, the duration is t1. This will be 2 VCC by 3 equal to VCC minus 2 VCC by 3 into e to power minus t1 divided by tau. So from here t1 will be tau into ln 2, and tau is, the charging time constant is Ra plus Rb into C ln 2. This is T1. Now we have to find out the duration of discharge, that is T2. Okay, so the instant when discharging starts, the voltage is 2 VCC by 3. So in the duration of discharging, the initial voltage will be taken as 2 VCC by 3. The initial voltage is 2 VCC by 3, and since it discharges towards 0 volt, so the steady state voltage, although it does not go to the steady state voltage, still the steady state voltage will be the voltage towards which it discharges. Although in between there is another transient, but for this transient, the steady state voltage of this transient will be the voltage when this circuit is left for infinite time in this transient only. So V infinity equal to 0, and Vt we will take, Vt will be at this point, Vt is VCC by 3. Again we will write this formula, Vt equal to V infinity minus, okay, so Vt is equal to VCC by 3, and this T is nothing but the duration, not the absolute time. For example, the duration I have taken as T2. The absolute time at this point maybe this is different from T2, but in this formula we have to take the duration only. So after T2 duration, the voltage is VCC by 3, V infinity is 0, V0 is 2 VCC by 3 into e to power duration T2 divided by discharging time constant. So from here T2 will be discharging time constant into ln 2. T2 will be, the discharging time constant will be Rb into C. Rb into C ln 2. So the total time period will be RA plus 2RB into C ln 2. Hence the frequency will be 1 by time period. This will be 1 by RA plus 2RB into C ln 2. So all the values are given. You will put all the values. You will get frequency as frequency will be 5.653 kilohertz. So the main concept in 555 timer IC is the charging is through RA and RB and discharging is through RB only. Okay, charging starts when the capacitor voltage hit the VCC by 3 and discharging starts when capacitor voltage hits 2 VCC by 3. And in the charging time, output voltage will be high, and during the discharging time, output voltage will be low. But the frequency of both output voltage and capacitor voltage will be same. Okay, in this question, the input voltage is varied from 0 to 100 volt, and the two Zener diodes are connected in series. And the voltage and current characteristic of each Zener diode is shown in this figure 1. This is figure 1 and this is figure 2. The input voltage is varied from 0 to 100 volt. So then now in the question we have to answer that which diode will be broken. The options are only D1, only D2, both D1 and D2, and in the D option none of D1 and D2. So let's say this is the current voltage characteristic. This is voltage and this is current. This is the current voltage characteristic. So let us first understand the meaning of current voltage characteristic. Let's say this is given for minus 80 volt for diode. This is for diode D1. It means in this region the diode will not be broken down. Diode is not broken, and if voltage across this diode is more than 80 volt in reverse bias, this will be broken down, and the current, normally we take this line as, or we think that the meaning of this line is if the diode is broken, the current through it will be very high. But this is a misinterpretation of this line. This line says that the value of current, if the diode is broken, the value of current may be anything between this value to this value. The current can take any value between the starting to the end values. The value of current will depend upon the external circuit. It is not decided by the Zener diode. The meaning of this line is not that the current through Zener diode will be very high or it will increase, the magnitude will increase rapidly. The meaning of this line is the current may be anything from this point to this point or even higher values. It will depend upon the external circuit. Like if I take 50 volt here and we have a Zener diode of 40 volt, and let's say this is 10 kilo ohm. Okay, so obviously this will be broken. The breakdown of Zener diode will occur and 40 volt will occur across it. So this will be our circuit, 40 volt, and here we have a resistance of 10 kilo ohm. Now the voltage across resistance is 50 minus 40, 10 volt divided by 10 kilo ohm. It means you have a current of 1 milliampere. So the same 1 milliampere current will flow through resistance as well as through the Zener diode. So how did we calculate the current through Zener diode? It is not decided by Zener diode. Instead, it was decided by the resistance here. So the current through Zener diode, when it has been broken down, the current through Zener diode will be decided by the external circuit, that is the voltage, input voltage and the resistance. And when the Zener diode is not broken down, this current will be very low. This may be in microampere. Okay. So my purpose is to explain you that meaning of this line is not that the current will be very high. It means that current may take any value between these values. Okay. The another thing is the two switches are connected in series. So it is very clear that the current through, it doesn't matter which diode or both of them are broken. It doesn't matter. In each case, current through both the diode will be same. Okay, ID will be same. And let us assume that for some voltage, let's say we have 30 volt or any voltage between 0 to 100 volt, there is some value of current that is flowing through diode D1 as well as through D2. And let's say that value of current is, I'm not taking any numerical value, instead I'm showing in the graph only. I'm showing some height for that value of current. This current is flowing through D1 and D2. Now you have current voltage characteristic of D1 as well as current voltage characteristic of D2. Let's say if you have a current voltage characteristic, it means if you have the value of current through this diode D1, with the help of current voltage characteristic, for that value of current you can easily find out the voltage across this diode. Let's say this is the current through diode D1. So what will be the voltage? If this height is the current, this width will be, this will be the voltage across diode D1. Now the two switches are connected in series, so the current through both the diode will be same, and let's say this height represents the current. So what will be the voltage across diode D1? The characteristic of D1 is this. Okay, and this characteristic cuts the current at this point. I have taken an arbitrary height of current, and for that height of current I am trying to calculate the input voltage requirement. Okay, so for this arbitrary height of current, this height cuts the first characteristic at this point. So the voltage across diode D1 will be, this will be represented by this width. If this width is minus 80 volt, let us take this will be at, this will be, let's say 10 volt, 10 volt in reverse wise. Okay, and the same current we will have to take the same height for current that is flowing in D2 also. So the same height cuts the characteristic of D2 at this point. The voltage across D2 will be approximately 0. So the total voltage, the total reverse bias voltage across D1 and D2, by adding we are getting minus 10 volt. So we can conclude that if the input voltage is 10 volt here, the total input voltage is 10 volt, approximately this height of current will flow through each diode. We are at this point and this point, and for both the diode, this height of current cuts both the characteristic in the region when neither of the diode has been broken down. Now let us increase the value of current, because the voltage is being increased from 0 to 100 volt. Now let us take this height of current. Let's say this current is I2. So I2 cuts the first characteristic, the characteristic of D1, let's say at this point. Although there is a range, it has overlapped. but ideally it will cut on a single point. So this is the voltage across diode D1. Let's say this is minus 80 volt, this is minus 40 volt. So voltage across this diode is minus, it means this is positive, this is negative, 40 volt. And the same height, the same current will flow through D2 also. So the same height will be taken for D2, and this height intersect with characteristic of D2. For finding out the reverse bias voltage across D2, we have to find out the intersection of current I2 and the characteristic of diode D2. So it intersect at this point. Again, the voltage across diode D2 is negligible. Okay, so the total voltage will be this voltage plus this voltage. So here V1 was 10 volt and V2 is equal to 40 volt. Okay, so when you have a voltage of 40 volt, none of the diode will be broken down. Now let us consider I3. Let us consider I3 when the diode D1 has just broken down. In the question, if you will see the diagram carefully, the height of current, that is I3, now I am taking the third current I3, the height of current I3 when the diode D1 has just broken down, this height will intersect the characteristic of diode D2, that is very near to origin, and it is also evident from this figure only. Okay, now let us consider I3 and let us try to find out the voltage corresponding to this height of current I3. So I3 intersects characteristic of D1 at this height, at this point. So obviously at this point the voltage across D1 will be minus 80 volt. It means this is positive, this is negative, and this will be 80 volt. And the same height intersects the characteristic of D2 at this point. It means the voltage across D2 will be, it is still negligible. Let's say this is 5 volt. Okay, let's say this is 5 volt. Okay, so the total voltage will be 80 plus 5, the input voltage will be 85 volt. So generally we have a thinking that if diode D1, if the two diodes are connected, Zener diodes are connected in series, or the two switches are connected in series, one diode has breakdown voltage V1 and the second diode has breakdown voltage V2. The overall breakdown voltage of the composite switch will be V1 plus V2. If you will think this way, the breakdown voltage of first diode is 80 volt and the breakdown voltage of second diode is 70 volt. This will come out to be 150 volt, and we will say that if 150 volt is connected, then only diodes will be, both the diodes will be broken down, otherwise no diode will be broken down. But in this question the voltage and current characteristics are different, that's why 150 volt will not be required to break down these diodes. Instead, a voltage, even when the voltage is less than 150 volt, at that voltage also switches can be broken down. So what is happening in this case? You are increasing the reverse bias voltage. If you will increase the reverse bias voltage, the reverse bias current will, the magnitude of reverse bias current will increase. At low reverse bias there will be low value of current. If you keep increasing the reverse bias voltage, the reverse bias current will keep increasing, and by finding out the magnitude of reverse bias current, you can find out the reverse bias voltage across each diode. Since the two switches are connected in series, so the reverse bias current through both the diode will be same. So the switch which has lower value of breakdown current will break down first, although the diode D1 has breakdown voltage. The breakdown voltage of diode 1 is greater than the breakdown voltage of diode 2. This is 80 volt and this is 70 volt. But the current has to be same, and the breakdown current of diode D1 is less than the breakdown current of diode D2. Okay. Switches are connected in series and breakdown current of diode D1 is less than the breakdown current of diode D2. So the diode D1 will break down first, and just at the verge of breakdown of D1, the voltage requirement of diode D2 is almost negligible. So we can say that if you will increase the input voltage more than 80 volt, this diode will be broken down. Now this diode is broken down and current may be anything on this line, but this current will be decided by external circuit, means other than this diode. So what is other than this diode in the circuit? The input voltage and the diode D2. So when the first diode has been broken down, current may be anything, but this current is limited by diode D2. Now again, if you increase the voltage beyond 85 volt, let's say for this height of current, the voltage requirement or the voltage across diode D1 is 80 volt and the voltage across diode D2 is 5 volt. So the total voltage requirement will be 85 volt. Now if you increase the voltage up to 100 volt, or let us try to break down the diode D2 also. So this is the point of breakdown of diode D2. So when D2 will be broken down, this will be the current. The minimum current required to break down the diode D2 is this height of current. Okay, and for this height of current, the voltage across diode D1 has to be minus 80 volt and voltage across diode D2 has to be minus 70 volt. So the total voltage requirement will be 150 volt. So the minimum voltage required for the breakdown of both the diodes is 150 volt, and if you are varying between 0 to 100 volt, only diode D1 will be broken down, diode D2 will not be broken down. So option A will be correct. An amplifier circuit is shown using PMOS and NMOS. The transconductance of this is M1, this is M2 and this is M3. The transconductance of this switch is, this transistor is, this is GM1, here you will have GM2 and GM3, and R01, R02 and R03 are the resistances of or the output impedance of these transistors. In the circuit we have to find out the voltage gain V0 divided by the input voltage, the small signal AC voltage gain. We have to find out gain V0 divided by V input. So to find out gain, let us first draw the AC equivalent circuit of each transistors. So in AC equivalent circuit of this amplifier, all the DC voltage sources are short circuited. So this will be short circuited, this will be short circuited, and the model of a MOSFET is modeled as, this is VGS and here we have a voltage dependent current source, transconductance into VGS, and the output impedance is connected in parallel with the dependent current source. This is R0. Okay. So let us consider this is the first transistor, the AC model of first transistor. This is G, this is S, this is S, and this is drain. Drain, source, gate, and source. This can also be connected. So for transistor M3, the G is connected to the DC source, and in AC circuit, DC is short circuited. So the gate of transistor 3 will be connected to ground. This will be grounded, and source of the transistor 3 is connected to V0. So the potential of this point will be, this is at V0 and this is at ground. So VGS will be 0 minus V0 here. This is at V0. For transistor M2, VDD will be short circuited, and this is gate. So gate will be short circuited. For transistor M2 also, gate is short circuited. S is connected to V0. Okay, to find out the small AC voltage gain, let us first draw the AC circuit of, or AC model of this amplifier circuit. So in AC model, all the DC voltage sources are short circuited, and instead of this MOSFET, we will draw the circuit diagram of, we will draw AC model of this transistor. So what is AC model of a transistor? Here we have VGS, and here we have a voltage dependent current source. This is GM, transconductance into VGS. This is drain, this is source, this is gate, this is source, and parallel to the current source we have a output impedance of this transistor, delta VDS divided by delta IDS. This is AC model of a transistor. Since this is a PMOS, so for PMOS this will be the source, this is gate, and this is drain. Okay, so for this PMOS, DC voltage will be short circuited. So if you will short circuit this, it means ground is connected to short circuit, G is connected to ground. If you see S is connected to VDD. This is also DC source, so S is also connected to ground. So for transistor M3, VGS is equal to 0 because G is connected to ground and S is also connected to ground. So VGS will be 0. If VGS is 0, no current will flow here, so this current will be 0. So transistor, in the AC model of transistor M3, we will have only R0, and this will be R03. So at the place of M3, in the AC model of M3, we will represent only R03 because this current is 0. So at the place of M3, we will represent only R03, and this R03 is connected between drain to source. R03 is represented between drain and source. So let's say this is source. Okay, this is connected to ground, and drain is connected to, this is connected to V0. Okay, this is our potential V0. Similarly, drawing the model of M2, this is an NMOS. So for this is ground, this will be source and this will be drain. So source is connected to V0, so I'm taking it as source. Gate is connected to VDD is short circuited, so gate is connected to ground. This is connected to ground. This is plus minus VGS of transistor 2. Here you will have a current source GM2 into VGS, and R02 will be connected between drain to source, and this is at V0. Okay, then coming to transistor M1, this is drain of, this is gate, this is NMOS, this is gate, source and drain. So drain is connected to V0, this is drain, and from drain to source we have a dependent current source GM1 into VGS1, and here we will have a resistance R01. G is connected to input voltage and S is connected to ground. This is ground and this is at input voltage. This is G and this is S. So VGS will be V input. So instead of VGS here we will write V input. Here what is VGS? The negative is connected to V0 and positive is connected to 0. So VGS will be 0 minus V0. So here the current will be, here VGS is 0 minus V0. So the current will be GM2 into minus V0. So current will be minus GM2 into V0. Again, if we simplify the circuit, because we have all the current source in terms of V0 and V input, so there is no need to show VGS now. We have R02, R03, R01, GM1 into V input, GM2 into V output and output voltage. So I am drawing the simplified circuit, more simplified circuit. This D is again connected to ground. This D is connected to ground. First drawing line for V0. Okay. This is at V0 voltage. R03 is connected between V0 and ground. This is R03. Then we have a current minus GM2 into V0 flowing from ground to V0. If you will remove the minus sign, the direction of current will be reversed. So the current is, we have a dependent current source and current is flowing, the direction of current is from V0 towards ground. So we have a dependent current source flowing from V0 to ground, and this is GM2 into V0. Okay, this is ground. So this is done. R02 is connected between V0 and ground. So this is R02. R01 is connected between, this terminal is nothing but V0 and this is ground. this is R01, and again we have a current source GM1 into V input flowing from, this is also V0, flowing from V0 to ground, and this is GM2 into input voltage. So if we further simplify it, it is very easy to visualize that R02, R01 and R03 are connected in parallel, and these two current sources are also connected in parallel. The first current source is GM2 into V0, second current source is GM1 into V input, and the equivalent resistance is R01 parallel, R02 parallel, R03, and this voltage is V0. So voltage V0 will be, here the current will be, or the overall current through this equivalent resistance is GM2 into V0 plus GM1 into input voltage. Since current will flow in upward direction, so the output voltage will be negative of this current into equivalent resistance, negative of current into this resistance. Let's say this resistance is x equal to V0. So V0 will be minus of GM1 into V input into X divided by 1 plus GM2, or V0 by V input will be minus GM1 into X. X is R01 parallel, R02 parallel, R03 divided by 1 plus GM2. Here we will have X also. If you will multiply, you will have GM2 V0 into X, and when you will take V0 common, you will have GM2 into X. So we will have GM2 into X here. Let's take it as X only. The parallel combination of three resistances, this is X. So this will be minus GM1 into X divided by 1 plus GM2 into X. This can be written as minus GM1 into X into 1 by GM2 divided by X plus 1 by GM2. If you will solve it, you will have 1 plus X GM2, and GM2 will be cancelled. So this can be written as this. You can solve it to get this expression. So this will be minus GM1 into, let's take this is resistance R1 and this is resistance R2, because GM is conductance, ampere divided by voltage. So 1 by GM will be voltage divided by ampere. This will give you the unit of resistance. So this can be thought as of resistance. So R1 R2 divided by R1 plus R2. So this can be written as the parallel combination of X and 1 by GM2. So this will give you minus GM1 into X is nothing but R01 parallel, R02 parallel 1 by GM2 parallel R03. It doesn't matter whether you are first taking parallel combination of R01 and R03, or means if you have to take parallel combination of 4 resistances, the order of taking parallel combination does not matter. You can take first parallel combination of these 2 resistance, or these 2 resistance, or R01 and R04. Okay, so the overall voltage gain is V0 divided by V input, okay, minus GM1 into R01, R02, minus GM1, R01, R02, R03, and 1 by GM2. C option will be correct. In this question, we have to find out a small signal input pole frequency. It means we have to find out the transfer function V0 S divided by V input S, and in the transfer function we have to find out the pole of the system. Okay. So first we have to find out the voltage gain or the transfer function of this amplifier circuit. So first we will draw the AC model of this amplifier circuit. For AC model, we'll first draw the AC model of this transistor. In the AC model we will have, this is G, this is S, and here we will have VGS, a voltage dependent current source. This is GM into VGS. RD is not given, this is not given, so we will take it as infinite. So we will not draw any resistance here. This is drain, this is source, and source is connected to ground. So this is ground. Input is connected to between the gate terminal is connected to 5 kilo ohm, and then input. This gate is connected to 5 kilo ohm, and then we have input here, and input voltage is always taken with respect to ground. So this terminal, between this terminal and ground, we can connect AC input voltage. Although I have shown the reference, this does not represent a DC voltage source. This is a small signal AC voltage source, and capacitor is connected between, this is drain and this is gate. So between drain and gate we have a capacitance, and this 1 kilo ohm resistance is connected between drain, and VDD is grounded. So VDD is grounded, it means here we have ground. This is 1 kilo ohm. Output is taken between D and ground. So this is D and this is ground. This will be output voltage. So we have a circuit diagram, and with the help of this circuit diagram we have to find out V0 S divided by V input S, the transfer function of this circuit. Okay, this is VGS, this is GM into VGS. Let us take this resistance is R1, and this resistance as R0. R0 equal to 1 kilo ohm and R1 equal to 5 kilo ohm. This is R0, this is R1. So we have to find out V0 S divided by V input S. So we will write down the equations. First we will write down this equation. In this loop, here you have a gain of input voltage. Let's say this current is I1. So V input minus I1 R1, and here you have a drop of VGS minus VGS equal to 0. This is first equation. Applying nodal at this equation, this current is GM into VGS, and in this direction current is, or this current is I1. So I1 gets distributed between this current, and here the current will be V0 divided by R0. So GM plus VGS will be GM plus VGS, this current plus this current is V0 divided by R0. The summation of these two current will be I1. So second equation, you have to find out relationship between V0 and V input. You have to find out relationship between V0 and V input, and you have variable I1 and VGS. Okay, so we have to eliminate I1 and VGS. So we need one more equation. Now applying KVL in this loop, here you have a gain of V input, or let us apply in this loop. Here you have gain of VGS, here you will have drop of I1 into impedance minus I1 into 1 by CS, and here you have a drop of V0. Okay, so from third equation, I'm not doing all the complete calculation. From third equation you can find out the value of GS in terms of I1. Okay, and that value of VGS can be put here. So this equation will be in terms of I1, and the same value of VGS can be used in this equation also. So from third equation, VGS will be V0 plus I1 by CS. So first and second equation can be written in terms of input voltage, output voltage, and VGS only. So value of the value of VGS we have found out from the third equation in terms of I1. So these two equations can be written in terms of VGS, can be written in terms of I1. So in this equation you will have I1, V0 and V0 only. So value of I1 can be found out in terms of, anyway, you have three equations. So with the help of these three equations, VGS, I1, these two can be represented in form of V0 and V input, V0 and V input. If you have value of VGS and I1 in terms of V0 and V input, using third equation you can find out the relationship between V0 and V input, and after the calculation you will get V0 S divided by V input S equal to R0 into CS minus GM divided by 1 plus CS into R1 plus R0 plus GM into R1 R0. With the help of these three equations you will get V0 S divided by V input S is equal to this. Now equating the characteristic equation to 0, you can get the value of pole. Pole is at S is equal to -1 divided by R1 plus R0 plus GM into R1 R0 into C. So the S is nothing but, this will give you the omega in radian per second. Frequency will be 1 divided by, you will have to divide it by 2 pi c into r1 plus r0 plus gm into r1 r0. So this will be 1 divided by 2 pi into c is 50 picofarad 10 to power minus 12. R1 is 5 kilo ohm, R0 is 1 kilo ohm plus GM is 0.01 into 5 kilo ohm into 1000 ohm. We have to keep the unit of kilo ohm. This is 5 kilo ohm, this is 5 kilo ohm. If you will take both the resistances in kilo ohm, you will have a unit of mega ohm. So take one resistance in kilo ohm and another resistance in ohm only. So this ohm into the unit of resistance in ohm and unit of conductance in Siemens. This will, after multiplication, these two quantity will make unitless, and here you have unit of kilo ohm. So kilo ohm and kilo ohm can be added. So this will be 10 to power 12 divided by 100 pi into, this is 56 kilo ohm, 56 into 10 to power 3, 10 to power 3, 10 to power 2, here you will have 10 to power 7, 10 to power 7 divided by 56 pi hertz. This is 10,000 divided by 56 pi kilohertz.